Swayam Prabha. Digital India. Educated India.
Welcome to 19th lecture of video course on Tribology. Today's lecture topic is fluid film lubrication. It involves mathematical analysis. It involves a merger, or we say marriage, of three equations. Equation number 1 is conservation of momentum, conservation of mass, and conservation of energy. We need to marry these three equations to get overall fluid film lubrication equation. Often we merge elastic deformation equation also along with this equation to get elastrohydrodynamic lubrication. Basic assumption in these equations is that gap between two metal surface or two material surfaces is infinitely small, maybe in order of micron. It can go up even the nanometer or in mm, but overall size also will grow accordingly or reduce accordingly. So, to start with that, you can say there is a classification of FFL as a fluid film lubrication. As I earlier mentioned, we can add fourth category, that will be elastrohydrodynamic lubrication. One more equation will come and give the right results. For elastic deformation or consideration of elastic deformation. So, let us see first three which have been used conventionally. First category says the hydrodynamic lubrication. In bracket it says the aerodynamic lubrication. The concepts remain same, only the governing lubrication media change. And hydrodynamic lubrication, it will be the liquid which will be used as a lubricant, while in aerodynamic it will be the gas. That is why to differentiate presence of liquid or gas, we say hydrodynamic or aerodynamic. Both of these mechanisms require two action. One is that there should be some viscosity. If viscosity is 0, then it will not occur, or we say solution will not be obtained using conventional equations. Another thing is a converging wave shape. There should be a convergence, there should be some inclination, there need to be a gradient which makes hydrodynamic or aerodynamic action or mechanism. Second mechanism is a squeeze film. This is basically governed by speed variation, and speed variation in direction of film thickness or changing the magnitude of the load or changing the direction of the load. There should be some sort of variation which brings squeeze film into action, or this mechanism will be accounted only when we have a load variation or speed variation. Viscosity also plays an important role in this kind of mechanism. Last one in this category is a hydrostatic. Again in bracket is written aerostatic. Hydrostatic for the liquid, aerostatic for gases. Here the pressure is supplied we need to provide external pressure to levitate one surface relative to other surface. As external pressure is supplied or applied, this will be a costly mechanism compared to squeeze film action, compared to the hydrodynamic mechanism. So, often we avoid hydrostatic or we provide only partial hydrostatic mechanism, unless no possibility of developing hydrodynamic action, no possibility of developing squeeze film action. There are number of methods to develop hydrostatic lubrication mechanism. We will be discussing those in detail when we start covering the topic on technology, or we say applications of tribology. To give a sketch of all these three mechanisms, I made the two blocks, the yellow color block and red color block. I am assuming this is the material 1, material 2, and there is a liquid. So, it is a basically for hydrostatic, and we are providing some relative velocity, relative velocity of yellow block with respect to red block. There is applied force, normal load. This may be a self weight, may be imposed from outside, or load to be supported. You can see there is a wedge action. Thickness on the left hand side, or fluid film thickness at the left hand side is greater than thickness at the right hand side, and this convergence is coming in the direction of velocity. So, this fulfills a hydrodynamic action. There is a normal load, there is a relative velocity, there is a wedge action, and we are assuming this liquid is viscous. Coming to the squeeze film action, again they are same blocks, the material 1, material 2, yellow block and red color block, and there is lubricant at the interface. Now, here we are saying the velocity is changing. Velocity of the second block is also changing, but not necessarily both the block have to have a relative velocity, need to have a velocity zone. If there is a velocity v 1 and there is no velocity v 2 and velocity v 1 itself is a fluctuating, even in that case squeeze film action will occur. Or if there is a load applied is initially maybe say 100 Newton, reduces to 80 Newton. Naturally, when load decreases, this block will move up. If loading increases, this block will come down, or say reduce the film thickness. So, indirectly even the load is going to induce the velocity of yellow block. So, whichever the situation is there, a squeeze film action will occur. If there is a relative movement of yellow block with respect to red block in the direction of film thickness. Last one is the hydrostatic. You see that we are feeding, we are supplying pressure or supplying liquid with the pressure. So, there is a pump which need to supply pressure to levitate this yellow block. Yellow block is carrying the load, right. As I mentioned, it will be the costly affair because using pump to lubricate requires energy. There will be consumption of energy as well as initial cost of the pump, maintenance cost of the pump. That is why it can be say is least preferred compared to squeeze film action, compared to the hydrodynamic action. Mostly fluid film lubrication equation start with the Reynolds equation. We discussed Tower's experiment in our earlier lecture. Tower was a person who could figure out there is some pressure generation if there is some inclination and viscosity of the liquid. And Reynolds, after learning from experiments of the tower, try to give mathematical justification, and that is known as a Reynolds equation. You can see this is a Reynolds equation. Left hand side are the pressure terms and right hand side are the source terms. When you are talking about the source, that means there is a possibility of first term which will make or which will induce a pressure between the interface or at the interface, maybe the first term, maybe second term, maybe third term, or maybe all together. And this equation was derived long back, maybe say around 120 years back. The only probability of solving this equation was low, not much mathematical calculations were available or computers were available. So, people used to think about simplification of this equation, because this equation is a partial differential equation. So, there are a number of estimations available, either rejecting this term or rejecting this term, rejecting one of this term, not treating all terms together. As we reject any term, we neglect any term, that equation will simplify it, and solving that equation will be simpler, right. So, we say there is a Reynolds equation and which can simulate all the behavior. The source term is 0, suppose the whole the right hand side is equal to 0, that is possible in hydrostatic lubrication. There is no velocity, relative velocity, there is no wave action, there is no velocity, relative velocity between the two surfaces in film thickness direction. So, for hydrostatic, this will be equal to 0. Coming to the hydrodynamic, there is a need of a relative velocity, there is a need of wave action, maybe in one direction or in both the direction. So, this may be in the x direction, this is in the z direction. We are neglecting y direction because y direction is a film thickness direction. Last one is a squeeze film, where the source term is in a y direction, while here we were neglecting for the hydrodynamic, while for squeeze film action we consider it. So, there is a possibility of only hydrostatic, only hydrodynamic, only a squeeze film action, or maybe all together, a combination, and that is generally happens in an engine bearing, where there is a relative velocity, there is a relative velocity in x direction, there is a relative velocity in a film thickness direction also, or because of the load it will change its position, shaft will change its position. So, we will give some sort of relative velocity in film thickness direction. We understand the Reynolds equation, but many times we feel how this equation was derived and what are the assumptions which were considered when Reynolds derived this equation, developed this equation. Because if we want to modify any of term, any of source term, or any pressure term or viscosity term, we need to know what are the assumptions, so that we can relax those assumptions, and in our system if those assumptions are valid we can keep same equation, if those assumptions are not valid we can relieve those assumptions. So, it is necessary for us to understand the derivation of this equation. This figure is a familiar in which we discussed in one of our lecture or earlier lecture. We say that if there is some sort of convergence, some sort of taper of one surface related to the other surface, they are not parallel surface, then velocity which is or liquid velocity which comes between two surfaces because of the relative motion of one surface over other surface. I am assuming this surface is suppose stationary and this surface is moving with a relative velocity of u a. Naturally, liquid which comes into contact with this moving plate will also start moving, and that is shown over here at the center. Velocity profile is a linear, while velocity profile here is a non-linear. Velocity profile at the exit is a linear, is a non-linear. Reason being, there is a pressure term which was added. We say at the exit pressure term will boost the flow, at the entrance it will retard the flow. But this was a this justification is from the physical point of view to understand it, but to quantify how exactly this profile will come, we need to apply mathematical principles. So, we can think about the mass conservation, or sorry, we can think about the force conservation at the start. Let us assume there is a this element at this position. As the liquid is a continuous, we can think about the continuum, and top surface is moving at the relative velocity compared to the bottom surface. So, we are assuming the shear stress on the top surface of the element will be more compared to shear stress at the lower surface, or we say that at this surface shear stress is more, that is why it is being given at the tau plus some gradient of tau, while at this surface there is no gradient, is only tau. For the force we have to multiply with the area. So, we are assuming that this is this area is a dx into dz, that is element. Coming to the pressure side, pressure is developed in this side. So, what we can start pressure into area, while here pressure plus pressure gradient, positive pressure gradient, because the pressure has been more. You can see over here pressure is increasing. Maybe quite possible if we develop a system, it will, after satisfying all the equation, it will turn out to be negative at the later part. But we do not want to prejudice about this, we do not want to pre-calculate. We say let us start with the mathematics, let us start with the conservation laws, and whatever comes out we will try to predict based on that. So, there is we are assuming there is a equilibrium. Now, you can see that we have not considered inertia term. Otherwise, if there is a element over here, it will be having inertia, and we should consider acceleration term multiply with the mass of this element. But our assumption is that inertia terms are negligible. Acceleration of this liquid will not be very high, and mass is also low. So, inertia terms are neglected. That is the first assumption in a Reynolds equation. We do not consider inertia term. Now, continuing with this, we say that we are considering conservation of momentum, and for time being we are considering only the force balance, and force balance in x direction can be given by this relation. The P into area, tau plus gradient into area, pressure plus gradient into dx into area plus tau into area. We know this tau dx and this tau dx will be cancelled. P dy by P dy dz and P dy dz will be cancelled. So, overall equilibrium comes with a gradient terms like this. See, I am rearranging equation, the gradient of shear stress, gradient of the pressure, and interesting thing, they have a same unit. Pressure and shear stress will have a same unit, x and y will be having same units, and there is a volume of element. This can be written or rewritten something like this: gradient of shear stress induce pressure or may increase pressure. So, we are emphasizing here the this tau is playing important role, and in liquids we know viscosity will play important role to induce this shear stress. The only question comes how to determine this tau. What is the mechanism of determining the tau? We already studied about the liquid lubricant. We say we can consider the Bingham liquid model, we can consider the non-Newtonian model or Newtonian model. A simplest one for Reynolds equation is a Newtonian model. What Newtonian model says, tau shear stress in liquid is equal to viscosity into velocity gradient. If I use this equation, in equation number 1, we can get pressure in terms of velocity and viscosity. If any of this is 0, if viscosity is 0, we know the pressure will not be generated, or if there is no relative velocity or there is no velocity gradient, then again there will be 0 pressure. So, that is why for hydrodynamic action we require both. We require viscosity, we require velocity gradient, we require relative velocity. If there is a relative velocity, velocity gradient will come. So, we can list down the assumptions what we have already made. We have not considered inertia term. So, we are saying it has a negligible inertia or fluid has a negligible inertia. So, the first assumption. Second, we have not considered the pressure gradient in direction of film thickness. You can see pressure gradient only in x direction. Maybe later we will consider pressure gradient in z direction. The film thickness direction, this is a y direction. We are not considering any pressure gradient term. What we are assuming, in that small space, small gap, pressure will remain constant. It is not going to change. There will not be any gradient on pressure. And last assumption in the what we considered here, that was a Newtonian fluid. Our fluid is governed by Newtonian law, or its shear stress is proportional to velocity gradient, and constant of the proportionality is viscosity. These are the 3 assumptions which we are making to drive equation number 2. We continue it, is a same force balance equation has come. Now, we can make another assumption. So, that I am assuming viscosity is not function of y. That means, a viscosity remain constant from bottom plate to the top plate, which is a slightly unrealistic assumption, because we know there will be a thermal heating because of shearing, and liquid is a liquid has a strong function between viscosity and temperature. So, viscosity will continuously change with the temperature, but we have not considered energy equation, we have not considered the temperature. So, there is no point to consider viscosity variation for Reynolds equation or to drive the Reynolds equation. So, that is why there is assumption viscosity is constant, it is not a function of y, it remains constant throughout, and of course, it is not a function of x and it is not a function of z we consider in the Reynolds equation. So, with this modification we can say rearranging equation, pressure gradient is equal to viscosity into velocity gradient of second order. Similarly, the way we have done in x direction, similar force balance can be done in z direction also. The equation will be pressure gradient in the z direction is equal to viscosity. We are assuming that there is no change in viscosity in x direction or z direction, and velocity gradient of second order velocity gradient is coming over here, right. So, there is a velocity u in x direction, velocity w in z direction, and y is the direction of film thickness, where the this velocity gradient is acting. So, this is the fourth assumption what we made. It is a constant value of viscosity, velocity is not a function of x, y, z. So, we have added first assumption was negligible inertia term, second assumption no pressure gradient in y direction, third assumption Newtonian fluid, and fourth assumption is a constant value of viscosity, which is a unrealistic assumption, but for simplification to understand the physics of or to understand the mathematics of FFL, we need to account initially, and so later we can modify this or we can relax this assumption. Now, we expressed pressure in terms of velocity, and we know velocity are known to us. What will be velocity of the bottom plate and what will be the velocity of top plate. So, it is easier for us to integrate velocity and get the pressure terms using boundary condition which are already specified. So, for this purpose we find to find the flow velocity or velocity of the liquid, we integrate this term equation 3 and 4th. Equation 3 was for x direction, equation 4 for the z direction. Now, when we integrate the first time, we are getting first integration constant, you can see, and velocity gradient is a pressure gradient into y film thickness plus one integration constant. Now, we can integrate this equation 5 second time and we find this relation, say eta into u. This pressure gradient is not depending on y. So, this y will turn out to be y square by 2. This C 1 is a constant, it is not a function of y. So, simply this will be C y plus another integration constant C 2. Now, we have a two velocity condition available to us. We can substitute or we can use those boundary conditions to find out value of C 1 and C 2. What are the boundary condition given to us? We say top plate has a velocity u 1, yellow plate has a velocity u 2. In earlier diagram we showed a u a, that was a relative velocity, that means u 1 minus u 2. And we are assuming over here that there is a slight tilt, but y is equal to 0 or our coordinate system is also inclined along with this plate. When y is 0, that means somewhere this point, velocity is equal to u 2. When y is a film thickness equal to film thickness, it can be in any cross section, y is equal to h, that time velocity is u 1. So, what are the conditions? We are assuming there is a no slip at the liquid solid boundary condition or junction, there is a no slippage. Whatever the velocity of the plate, same velocity is imparted to the liquid, not a single or not a 0.1% variation in the velocity, same velocity is being imparted to the liquid when there is an interface, right. So, we can add this assumption also. Say initially we assumed inertia terms are negligible, second was a pressure gradient in direction of film thickness is negligible, we are not accounting it. Our pressure gradient in x direction as well as z direction does not depend on the y coordinate. Then Newtonian fluid, we assumed constant value of viscosity, the viscosity is not function of x, y, z coordinates. And last assumption what we made here is that there is no slip at the liquid solid boundary. If we use this kind of slip condition, then expression will change, and for most of the time the liquid case this assumption is justified, but this will be a problem particularly gaseous lubrication. In gaseous lubrication there will be some slippage which need to be considered. Many times we say first order slip, second order slip, that can be considered when we develop this equation for air bearing or gas bearings, right. So, what we considered in previous slides, this equation we derive this equation 6, we considered two boundary conditions. Now, we substitute y is equal to 0 and u is equal to u 2. So, this this term will be 0 as is multiplied with 0, second term also will be 0, third term C 2 will be equal to eta into u 2. So, we got integration constant C 2 is equal to eta into u 2. Now, time comes to find out the C 1, we can use another boundary condition. See, when y is equal to h, u is equal to u 1. As we already know what is a C 2, we can substitute C 2 value over here. So, eta into u 2. Already there is a term eta this side. So, we can bring u to this side and say it will be u 1 minus u 2. This is a known term for time being to us, and then we can determine C 1. We say that C 1 is equal to velocity gradient, pressure gradient and flume thickness. We have C 1, we have C 2, and we can substitute in equation 6 to find out velocity profile. On substitution, we find this result. Now, we can match this result with our earlier expression. So, when y is equal to 0, u is turning out to be u 2. That is the same boundary condition, we have not made any mistake. When y is equal to h, so this is same again 0, this will be 1, h by h is 1. So, u 1 minus u 2 plus u 2. So, this will be u 1. So, this shows, and we have done a right job, we have not committed mistake. And another thing is that maximum velocity is u 1, minimum velocity is u 2. In between, the pressure is going to be accounted. Pressure gradient will be lower at the entrance side and will be positive on exit side. So, we will be getting some pressure profile, velocity profile. And another thing is that we have two velocity terms. If we say there is a u 2 is a 0, then only there will be one velocity term and one pressure term, or whatever assumption or hypothesis was there, because of inclination there is a boosting of the pressure or boosting of the flow at the exit and a retardation at entrance. So, same thing is coming from mathematical treatment. We can see what we have initially hypothesized. This plate is inclined, this plate is a constant or the horizontal. Because of this inclination, at this when maximum pressure occurs, when velocity gradient is 0, the velocity pressure gradient is 0, we are finding the linear profile. You can just get the same result over here. For maximum pressure, we can substitute equal to 0 dp by dx. When it is 0, then we are going to get velocity profile, simple profile. We can find out at any h what will be the this term plus u 2, and we can find a linear profile. While when there is a finite value of dp by dx either negative or positive, we can get this result, this side result, right. So, this is indicated, and in this diagram, as I mentioned earlier, there is a term u a. u a in this case is equal to u 1 minus u 2, that is the velocity term. And in when we use a relative velocity term, naturally we have to make other plate as a 0 velocity. We transfer u 1 u a here, and u 2 will be 0. That is a relative velocity which we are considering. We are considering only the difference in velocities. We are not interested in absolute velocities, right. So, what we can mention, or what is mentioned particularly in this slide, is the Poiseuille flow terms retard the fluid flow at the entrance as shown in this figure. The pressure term boosts the flow at the exit. You can see that additional velocity term are here. And so, we can say that it is a conserving momentum, as well as there is a force mass balance given to this. Same expression what we have done in x direction can be derived for the z direction. Almost the same treatment, there is a velocity pressure gradient in x direction, here pressure gradient in z direction. So, y square remains same, y h remains same, 2 eta remains same. Here velocity is terms is coming. So, velocity in in x direction, here it will be the velocity in z direction. Initial velocity of the plate, obviously not initially, the velocity of the lower plate in x direction, velocity of lower plate in z direction. So, we have now the pressure term, we have a velocity term in terms of the pressure. We can find out inverse of that, we can figure out what will be the pressure in terms of velocity. To do that, we require equation or additional equation, what we call as a conservation of mass, or many times use the word continuity equation. So, that comes out here, this conservation of mass. We are making one assumption that density is not changing, is not getting is an incompressible liquid. So, density will not depend on x direction, z direction or y direction. With that kind of assumption, we can simplify continuity equation or mass equation in this term: velocity gradient in x direction, velocity gradient in y direction, z direction, and this is given a figure over here. There is an element over here, and we are considering 3-dimensional model: z direction, x direction as well as y direction. This will be equal to 0. In previous slide, we have a expression, or we figure out the expression u in terms of pressure, as well as we figure out w in terms of pressure. You can substitute these values, those expressions, and then find out other equation or merge momentum equation in this continuity equation, right. However, we have made one assumption over here, that is the incompressible fluid. That is why we want to add this. Now, the assumption list is increasing. First assumption was a negligible inertia term. Second assumption was a negligible pressure gradient, excuse me, Newtonian fluid, constant value of viscosity, no slip at the liquid solid boundary, neglecting angle of inclination for the coordinate system. For time being, or we can relax all these assumptions, and final assumption in this case is incompressible fluid. For air, for gases, we need to account viscosity density variation in coordinate system. So, we need to account this equation, and we can substitute expression of u, expression of w, but there is a velocity gradient in y direction also. So, we need to integrate from 0 to h from complete for the complete film thickness. 0, there is a lower the coordinate system is placed at the lower plate, and h where the thickness is measured at the upper plate. So, there is h. Now, we are integrating with respect to y, because the gap we are assuming is in y direction. Here when we integrate the dy dv by dy into dy, we will get velocity as a dv. This expression will be relatively easier for us. This will be slightly complex, this will also be slightly complex. This expression is very simple, right. What we earlier derived u in terms of y and in terms of x, with assuming that there is some pressure, but coordinate system x and y, and when we substitute here, we are getting both the things, we are getting x as well as y. Similarly, velocity in z direction is coming in relation with y and z. Here the z and y both are involved. So, we need to use some sort of a special treatment to integrate this equation this term and integrate this term. As I mentioned, this integration of this term is simpler, there will not be much problem for us. Now, we can use a Leibniz rule. What is say that we can go ahead with partial integration, or we say the step by step integration, when we know the u itself is a function of y x, and we need to differentiate as well as integrate it. So, we can take out this term out, say assuming this term is a u dy, but we need to subtract and add u at the b value, what is the value of the u at b, and differentiation of b with respect to x. Similarly, what is the value of a, value of u at a, and differentiation of a with x. So, this is a well established rule, we are using it for our purpose. When we use this relation, what we get? This differentiation term is coming out, there is a u into dy minus, because b is h in our case. So, it will be differentiation of h with respect to x minus, instead of a we have a 0 value over here. So, differentiation of the 0 will not be there, this term will be neglected or will be z plus 0 and then can be neglected, can be removed. So, what we say, this term can be replaced with these two terms. We can substitute back these terms and proceed further integration, right. So, I am just rearranging it. We know u at the value of h is a boundary condition, that is a u 1. This is a gradient term and there is a integration term. We can substitute this, and there was another term, the integration of u with respect to y from 0 to h. When we integrate this term, what we are getting? We are assuming dp by dx is not a function of y, u 1 and u 2 are not function of y, and h is also there, which we can integrate. We say that when we integrate u, there will be y, and integration limits are h and 0. So, it will turn out to be h minus 0, and that is why there is h. I will just repeat it. So, when we are integrating this is the y term, the y square. So, integration of y square will be y cube divided by 3. There is a term y, h is constant, the integration of y will be y square by 2, and this 2 eta is taken out, is a common. Pressure gradient does not depend on the y, and there is a integration limits are h and 0, plus this velocity is not function of y, h is in this case we are saying that is a constant, it is not a function of y over here, and y is coming over here. So, it is a y will be replaced with or integrated like a y square by 2. There is a no term related to y, u 2 is constant. So, it will be u 2 y, and as I say the integration limits are h and 0. So, h minus 0 will be equal to h, will be u. The overall this term will turn out to be plus u 2 h. Now, we can substitute values at h and values at 0, or a value of y when it is h equal to the h, or value of y when it equal to 0, or we say y is equal to h or y is equal to 0. When we substitute this, what we get, this overall term from this is a minus h cube by 6, while from this it will turn out to be h square by 2, and this third term is a u 2 into h. Rearranging this equation in more systematic manner, we say that this is the first term, pressure term is a minus h cube by 12 eta pressure gradient plus term related to h, and there is a relative velocity, and last time is coming the absolute velocity of a lower plate. Further, we can rearrange this term, and what we get overall this equation number 11. There is summation of velocities and there is a pressure term. So, velocity term and pressure term. Now, we drive this equation, and we have previous equation number 10. We have done this work, we have integrated over here. So, that is available to us. This is already constant, or it is not going to be integrated. So, we have one term which need to be differentiated. So, this term will be differentiated. We substitute here in equation, what we get over here is something like differentiation, and this is the same term minus u 1 pressure wedge term, or we say that gradient of from thickness. Now, we can differentiate, as we know dp by dx depends on x. We have already made assumption eta does not depend on x, but h may be depending on x. So, we need to rearrange, and sometimes we say that there is a possibility of u 1 and u 2 depends on h. There is a possibility. Some typical examples are the rubber bearing, when there is a stretching action. That is why we use a term for u 1 and u 2 as a stretching term. we say this is the same term which we were written in the previous slide, and integrating or differentiating, we are first bringing this term inside, because there is a common dou y and dou by dou x that is taken as a common. We are bringing h into this bracket, rearranging equation, and then what we are getting something like this, right. So, still we need to differentiate it, but there is a term pressure gradient is remains same, and velocity term due to this addition or due to this subtraction is getting changed. There is a relative velocity, and that is negative relative velocity. We say in this case is the u2 minus u1. We know the u1 is greater than u2. So, it will be a negative term, or both will turn out to be negative, negative can be taken out. Now, but this equation was derived based on the Leibniz theorem or Leibniz law. We can do alternative method also. We can use alternative method to get whatever we have assumed or solve the equation is the same or not. We have alternative method to develop or drive the equation 12. What that says, we have velocity. Now, we need to differentiate this velocity, right. Then differentiation here, y and x, there is no relation as such, they are independent coordinates. So, differentiating y with respect to x will not give any result. So, it is a 0, and differentiating h with respect to x gives a velocity gives a wage term to us. That is why this after differentiation will come like this. Here we are taking by parts, only the first bracket was the differentiated first, then second term need to be differentiated, keeping first term as a constant, the same term. Here the second differentiation comes second derivative of p with respect to x. When we are differentiating this term, we have h term also, and we can differentiate h as this is the inverse. So, it will be minus sign will come, and this expression will turn out to be y minus h square plus or multiple along with this. Now, here we are saying that u1 and u2 also may be differentiated with respect to x. When rearranging this equation, because there is a pressure term here, there is a pressure term here, and we need to we can rearrange later maybe, but once we first in this case we have integrated. When we have velocity gradient, it can be integrated with respect to y, because there is a y term over here. When we integrate it, what we get as such the dh by dx is not depending on y. So, there is a simple integration of y, it will turn out to be y square by 2. So, this term is turning out to be minus h square by 4 eta, because integration limits are 0 and h. That is why we say that this is overall minus h square divided by 4 eta. This is same term, this is not going to change with y. Coming to the integration of these two terms, what we can say that there will be h cube divided by 3 minus y the h cube divided by 2. When we take common, it will turn out to be minus h cube. That is why the term is coming here minus h cube divided by 6. 6 into 2 will be 12. That is why this is written here minus h cube by 12, and second gradient of the pressure, right. And this is again there is a y, we can integrate this y, and it will turn out to be it will turn out to be h square by 2. Here h square will be cancelled out with h square, it will turn out to be overall minus 1 by 2, and this term will remain same, right. Now, time to rearrange the equation. What we are saying, rearranging the equation is that there is a second derivative of the pressure, there is a first derivative of pressure. We can rearrange in a such a manner that there is a one gradient terms comes out, and h and dp can be retained. What we are saying here in this case, if I assume there is a term, and now we want to integrate we want to differentiate by parts. When you differentiate first only this term, What will be this one? Minus 3 h squared divided by 12 eta. 3 will be cancelled with the 12. So, it will turn out to be minus h square by 4 eta into dH by dx. This pressure term will remain same. When you integrate second term, keeping a minus h cube by 12 eta constant, that is over here, and we will get a pressure term, second derivative of pressure. So, these two terms can be rearranged in this term, and this is the same what we have obtained previously without with the Leibniz law. And if you do not use the Leibniz law, but directly we use simple our straight equations, we also get the same expression. So, there is no problem in derivation of this. Now, we have done in x direction, similar expression comes in will be we can be pointing out, or we can get in a z direction. So, same expression, similar relation in z direction is something like this, minus instead of x there will be z, it will be the gradient in z direction, h will remain same, this term will remain same, this term only the x will be replaced with the z, and here x will be replaced with the z, and u1 will be replaced with the w1, u2 will be replaced with the w2, right. So, we got a term in x direction, term in z direction. Now, we can substitute these relations in this continuity equation, which was integrated to get the results. When we substitute this equation 12 and 13 in this equation, what we get? Something like this. After substitution, what we are getting, the first pressure gradient with h cube 12 eta and dp by dx, plus second term, this term, and this we know this expression is simple. We know integrating v will give me v at the h and v at 0. Lower limit is 0 and h is upper limit. So, velocity at the velocity of upper plate and velocity of the lower plate in y direction. Then comes this third term. Third term is can be represented or can be written something like this, which is the same equation. Now, we can rearrange this equation. There is a this term and this term has a lot of similarity, and these are the both of the pressure terms. That is why we can take other side and we say pressure term in x direction, pressure term in z direction, and these are the partial derivation of the second order. While this equation is on this side, here the negative term is replaced, or maybe we are taking inside negative term, then minus u1 plus u2, that is written over here, u2 minus u1 into h plus this term v h minus v 0. Similarly, this negative term has been replaced with the positive term. We are saying that half this and the w 2 minus w 1. If you remember, this is same what we have done, what we started as a Reynolds equation. This is the same term, right. Now, we can give some names to these terms. What we say, this is a pressure term which need to find out the pressure after solving this equation, and these are the source terms. This source term u 2 minus u 1, if considered this variation is changing with respect to x, then it will be called as a stretching term, stretching action. We say that u 2 and w 2 and minus w 1, this relative velocity is changing with z, then it will be stretching term, and it happens in micro motion at the rubber level, when there is elastic deformation and two particles are even though of the same body, they do not have the same velocity. Generally, for the solid motion, this gradient turn out to be 0. For steel, for the barbate material, this will not be counted. To some extent, when there is a plastic flow or there is a viscoelastic flow, then this terms will be there. We say that velocity gradient along the z direction, along the x direction, and velocity gradient along the z direction. Generally not possible, but will come if there is a viscoelastic flow or viscoplastic or plastic flow. Maybe say polymer bearings also, polymer it can be accounted. There is another term what we call the wedge term. So, there is a change in the film thickness along the x direction. Similarly, change in film thickness along the z direction. So, these are the wedge action or wedge terms need to be there is a essential need for these terms to develop hydrodynamic action, or we say we require inclined surfaces to find the hydrodynamic action. And in short, it has been represented something like dou h by dou x, dou h by dou z. They need to be finite, or either of this term need to be finite to develop hydrodynamic action. Last one is a squeeze action. We say that bearing surface move perpendicular to each other. In this case, or we say that film thickness h is continuously varying. There is a separation, and because of the relative velocity along the film thickness direction, there will be change in film thickness, right. What we are talking, this thickness will move up and down. Now, as this diagram earlier we started, this is having a wedge action, and there is a relative velocity u with respect to the red block, then this is satisfying our this requirement, this hydrodynamic action. Similarly, this is squeeze action, what we initially divided, we say that there is a squeeze action because of this. There is a change in film thickness. The change in film thickness may happen if there is a relative velocity in moving up, this plate is moving up and moving down, there will be change in h, that is going to change, that will be a source term to develop pressure. Because of this change, because of the this is squeeze action, there will be pressure generation, or in other words, whatever the source term we choose, there will be pressure generation. This is a hydrodynamic action, this is a hydrodynamic action, this is a squeeze action. And as I mentioned that because of the velocity, this is film thickness is changing. So, many times what we write V1 minus V2 as a dH by dt, t is a time, h is a film thickness. So, derivative of h with respect to time, that brings viscosity variation with the time, and that is the same film thickness variation with the time, and that is the same thing which is given over here. So, we will continue with the Reynolds equation or some simplification of Reynolds equation in our next lecture. Thanks for your attention.